Ever imagine a world where unbreakable codes are cracked in seconds?
Yeah.
Or where we can design revolutionary drugs just molecule by molecule on a screen, or even predict climate patterns with crazy accuracy.
It's mind-blowing.
Well, that's the kind of future that quantum computing promises, right?
Yeah, it really does.
Almost feels like something out of science fiction, to be honest.
It does.
But on this deep dive, we're going to tackle this question that's on a lot of people's minds. Is this quantum revolution really just around the corner? Or is this something that's decades away? Still far off in the future?
You know, you brought in this awesome article from DevHooks,
Oh, yeah.
and it really gets into the nitty-gritty of this very question.
Yeah, for sure.
What we want to do today is pull out those core insights,
Yeah.
the really juicy stuff from the article, and give you a good understanding of where quantum computing really stands today
Right.
and what its potential truly means.
Yeah, and I think before we get too far into the when and the why of it all, it's probably worth just taking a step back and really nailing down that what,
I agree.
what is quantum computing exactly? Because we hear the term thrown around a lot, but what's the real core difference between the computers that we use every day
Right.
and these quantum machines? What makes them so special?
It boils down to a completely different way of processing information.
Okay.
It leverages these really strange but super powerful rules of quantum mechanics.
Right.
Our current computers use bits,
Uh-huh.
those simple on or off switches
Yeah.
representing 0 or 1.
Right. Got it.
Quantum computers use qubits.
Qubits, yeah.
And this is where things start getting really interesting.
Okay, so
Qubits can exist in a state called superposition.
superposition. Okay, yeah.
Which-
Because that's where things get really mind-bendy, right?
Yeah,
That idea that a qubit can be a 0 and a 1 at the same
at
time.
the same time.
It's kind of like that light switch analogy that's both on and off until you actually look at it.
Exactly. Exactly. And this both-hand capability
Mm-hmm.
allows quantum computers to explore
Yeah.
just insane number of possibilities all at the same time.
Wow.
Think of it this way.
Okay.
If you are trying to find the exit in a maze,
Right.
a classical computer might try each path one by one,
Yeah.
but a quantum computer, thanks to superposition, can actually explore all the paths at once.
Oh, wow.
And then you have
Entanglement.
entanglement, right? It's
Yeah.
like that spooky action at a distance, right?
It is.
Where 2 or more qubits are linked,
Yeah.
and then the state of one instantly influences the others,
Immediately.
no matter how far apart they are. It's wild.
Wild. And
It's like flipping one of those light switches in one room, and then another one in a completely different building just instantly flips too.
it's like they're talking to each other.
Yeah, it's crazy.
And this combination of superposition and entanglement, it's like the dynamic duo of quantum computing.
It allows these quantum computers to perform these massively parallel calculations.
Right.
It's like a turbocharge for certain kinds of problems
Yeah.
that normal computers just choke on,
Yeah.
problems that are just intractable,
Right.
even for the most powerful supercomputers that we have today.
So this is where I think the DevHooks article starts to get really, really interesting.
It does.
Because it starts to explore,
Why?
yeah, the why.
Why does it matter?
Exactly. Why does all this potential computational muscle actually matter in the real world?
Right.
Because it's not just about bragging rights, right?
No, not at all.
About building the fastest computer.
It's about solving real-world problems
Exactly.
that affect people's lives.
So the article outlines some pretty transformative possibilities across a bunch of different industries.
Yeah.
And it starts with healthcare and drug discovery.
A huge area of potential.
So how could quantum computing change the game in those fields?
Well, the truly revolutionary thing here is the potential for, incredibly accurate molecular simulation.
Okay.
Imagine being able to design new medications by precisely modeling how they're going to interact with proteins and other molecules in the human body
Right.
before you even do any physical experiments.
You're simulating it on a computer.
Exactly.
Okay.
And right now, we largely rely on trial and error in the lab.
Yeah.
It's slow and it's expensive.
Yeah, for sure.
Quantum computers could allow us to virtually test countless drug candidates
Oh, wow.
and even design entirely new ones with specific properties,
Right.
leading to faster development of life-saving treatments
Uh-huh.
and truly personalized medicine tailored to an individual's genetic makeup.
Oh, wow.
Think about being able to simulate the intricate folding of complex proteins with an accuracy that's just impossible today,
Right.
potentially unlocking cures that we haven't even conceived of yet.
That's
A
incredible.
whole new frontier
Yeah, it really is.
in medicine.
So that's an incredible prospect, right? Like actually cutting down years of research and getting treatments to people so much faster.
And more effectively.
The article also goes into cybersecurity,
Yeah.
which feels like a bit of a double-edged sword when we talk about quantum computing.
It really is.
Right.
On the one hand,
Yeah.
the sheer power of quantum computers poses a significant threat to many of our current encryption methods,
Right.
the very systems that protect all our sensitive data online.
Yeah, for sure.
Quantum algorithms could potentially crack these codes much faster than classical computers.
So everything we think is secure now.
It might not be so secure in the future.
Right, okay.
However, the article also highlights this really exciting development of quantum cryptography,
Okay.
which uses the principles of quantum mechanics to create fundamentally secure communication channels.
So it's like a shield and a sword at the same time.
Exactly. It's based on the laws of physics.
Okay.
So any attempt to eavesdrop would inevitably leave a trace, alerting the communicating parties.
So you'd know immediately if someone's trying to listen in?
Yeah, you would know.
Okay, interesting.
It's like an unbreakable lock and key system.
So it's a race against time, right?
It is. It is.
Preparing for these potential vulnerabilities while also trying to harness quantum mechanics.
To make things even more secure.
Right, for even stronger security.
It's a fascinating dynamic.
Climate science is another area where the sheer complexity of the problem just seems tailor-made for quantum computing, right?
It does.
So how could it help us tackle something as vast and intricate as climate change?
Think about the sheer volume of data involved in climate modeling.
Right, it's massive.
From atmospheric conditions to ocean currents.
Yeah.
All of that data.
So much information.
Quantum computers could potentially process and analyze these massive data sets much more efficiently,
Okay.
leading to more accurate and detailed climate predictions.
So we could model these things better.
Much better. This improved understanding could then inform more effective strategies for mitigating the impacts of climate change
Right.
and developing sustainable solutions.
So it's not just about understanding what's happening.
No.
It's about then using that knowledge to actually do something about it.
Absolutely, to find solutions.
Imagine being able to model complex atmospheric interactions with far greater precision.
And that would give us
Right.
much clearer insights into future scenarios.
Wow. So we could actually anticipate things that are going to happen
Exactly.
and then maybe even preemptively make changes.
Exactly. It's like having a crystal ball for the planet,
Yeah, a little bit.
but a crystal ball based on science and data.
So that's a really hopeful application, right?
Yeah.
Offering this powerful tool to address one of humanity's biggest challenges.
Absolutely.
Then there are optimization problems, right?
Uh-huh.
Things like figuring out the most efficient routes for logistics and transportation,
Right.
or even optimizing those complex financial portfolios that can make your head spin.
It's all about finding the best solution
Yeah.
from a huge number of possibilities.
Right. And those classical algorithms just get bogged down in all that complexity.
They do. They do.
But quantum computers, with that ability to explore multiple possibilities at the same time,
Yeah, that's the key.
through superposition,
Exactly.
could potentially find those optimal solutions so much faster.
Much faster, more efficiently.
Leading to improvements in efficiency.
And resource allocation.
Right, across various industries.
Pretty much anywhere you need to optimize something.
So the why is pretty convincing, right?
Yeah.
The potential impact is huge.
It's huge.
But the burning question, and what the DevHooks article really focuses on, is how close are we to a quantum breakthrough?
Right. The million-dollar question.
Yeah, and it breaks down some of those major technical obstacles, right?
It does.
Starting with the fundamental challenge of just building reliable hardware.
Yeah, that's the foundation.
It's not just about stringing together more and more qubits, is it?
It's not that simple, no. As the article emphasizes, creating and maintaining stable qubits is a really, really tough challenge,
Right.
both for engineering and for physics.
Mm-hmm.
These quantum states are incredibly fragile,
Okay.
and they're super susceptible to any kind of environmental disturbance.
What kind of disturbances are we talking about?
Even tiny vibrations or
Yeah.
fluctuations in temperature
Really?
can cause errors.
So you have to keep them in these very, very specific conditions.
Exactly, they need to be pampered.
Okay.
In fact, to maintain their delicate quantum properties,
Yeah.
qubits often need to be kept at temperatures that are colder than outer space.
Wow.
It's really demanding.
And the article mentions Google's 2019 claim of quantum supremacy as a kind of significant moment in the
Yeah,
field.
it was a big deal.
So can you explain what that was
Yeah,
and why, while it was definitely a milestone,
it was a milestone.
it doesn't necessarily mean that we have practical quantum computers that are ready for everyday use.
Not yet.
So what was going on there?
What Google did was demonstrate a quantum computer performing a very specific calculation.
Okay.
It was a somewhat artificial calculation, to be honest,
Okay.
but they did it in a matter of minutes.
Uh-huh.
And theoretically, it would take the most powerful classical supercomputer thousands of years to complete the same calculation.
Wow, that's a huge
It
difference.
is a huge difference.
So they really showed that quantum computers could outperform classical computers for certain tasks,
For certain tasks, yes.
but not all tasks.
Right. And the specific problem that they solved wasn't directly relevant to real-world applications.
Okay, got it.
So the point is they demonstrated the potential,
Uh-huh.
but we still need to develop much more stable and error-resistant qubits to tackle those practical problems we've been talking about.
Right, the stuff that actually makes a difference.
Exactly. It was a landmark demonstration, but not the dawn of universal quantum computing.
Right, okay, so that leads perfectly into the next hurdle that the article discusses, error correction.
Ah, yes,
Yeah.
Senator, correct.
It sounds like these quantum systems are inherently prone to making mistakes.
They're sensitive little things.
So why is that such a big problem?
Well,
And what's being done to address it?
think about it. Even a small error in a classical computer calculation
Yeah.
can lead to a wrong answer.
Right, but those are pretty rare.
They are. But in a quantum computer with these super fragile qubits,
Uh-huh.
errors are way more likely
Okay.
because of all that environmental noise we talked about.
Yeah, so it's a much bigger problem.
It is. And if these errors aren't detected and corrected,
Uh-huh.
they can pile up really quickly
Oh, wow.
and completely invalidate the entire computation.
So it's like a house of cards.
Exactly. One wrong move and the whole thing collapses.
Right, so it's
Okay.
essential to catch and fix those errors.
Absolutely. Quantum error correction is absolutely essential.
So what's being done about that?
Researchers and companies like IBM and Google are investing a lot of resources
Okay.
in developing these sophisticated algorithms and hardware architectures that can actually identify and fix these quantum errors without messing up the underlying quantum state.
Right, without disturbing the whole delicate balance.
It's a delicate dance, for sure.
So that's a major area of research then.
It's a huge area. It's crucial.
Okay, and then there's just the sheer challenge of scaling up, right?
Yeah.
Because the article points out that we need to go from the hundreds of qubits we have now.
Which is already a lot.
Right, it sounds like a lot.
It is impressive.
To potentially millions to really tackle these complex practical problems.
Millions, yeah. It's a massive leap.
That sounds like a monumental technological leap.
It's a huge undertaking. It's not just about building more of the same fragile qubits.
Right.
It's about coming up with totally new breakthroughs in how to connect and control vast numbers of these qubits
Okay.
while maintaining their quantum coherence and effectively managing errors across the entire system.
Right, so you can't just copy and paste the same thing a million times over.
And no, it's got to work together seamlessly.
You need new approaches.
Exactly. Researchers are exploring different materials, different architectures,
Okay.
new ways of entangling and controlling these qubits.
That's fascinating.
It's like building a city
Wow.
where every single component needs to operate in perfect harmony,
Right.
despite being incredibly sensitive to its surroundings.
It's a huge coordination problem.
It is. It's a massive coordination problem.
So with all this intense research and development happening,
Yeah, it's a lot field.
who are the key players in this quantum computing race, right?
Right. Who's leading the pack?
Because the DevHooks article names several companies and organizations.
Yeah, it does.
So who are the big names in the game?
Well, there's IBM Quantum.
Okay, IBM, yeah.
They're making big strides in making quantum computing accessible
How so?
through these cloud-based platforms.
Oh, interesting.
They're focused on developing fault-tolerant quantum systems.
Okay, makes sense.
Then you have Google Quantum AI.
Google, of course.
They're pushing the boundaries of qubit stability and scalability.
So they're really trying to make those qubits more robust.
More robust,
Yep.
exactly.
And then Microsoft is in the game too.
Microsoft is taking a different approach.
Okay.
They're working with topological qubits.
Topological qubits?
Yeah, it's a bit more complex,
Okay.
but they believe it offers more resistance to certain types of errors.
So they're trying to address that error correction problem head on.
Head on, exactly.
And then we have D-Wave.
D-Wave is focusing on quantum annealing,
Okay.
a type of quantum computing that's particularly good at solving those complex optimization problems we talked about.
Right, like finding the most efficient route.
Exactly, that kind of thing.
So they have a specific niche.
They do, they do.
And the article also mentions some exciting startups,
Yeah, the up-and-comers,
like IonQ and Sequantum.
they're exploring new and potentially very scalable quantum architectures.
Interesting. So they're kind of like the dark horses in the race.
They could be. They're coming in with fresh ideas.
Okay, so it's a very dynamic and competitive field, right?
It is. It's a very exciting time to be in quantum computing.
With all these different players and all these different approaches.
Everyone's trying to find the winning formula.
So given all these efforts and all the progress that's being made, what kind of timeline are we realistically looking at before we see more of a widespread impact?
That's the question, right?
Because the article does touch on some expert predictions.
Yeah. It does.
So what are people thinking?
Most experts believe we might see what's called quantum advantage
Quantum advantage, okay?
within the next 5 to 10 years.
So that means quantum computers will be able to solve specific practical problems faster
Or more efficiently.
than the best classical computer.
Exactly.
Okay.
But achieving a fully fault-tolerant quantum computer,
Which is what we really need.
it's the holy grail.
One that can reliably perform complex calculations for all sorts of applications consistently and accurately.
That's the dream.
That's probably further down the line.
It is. It's likely to take another decade or maybe even longer.
So we're making progress, but there's still ways to go.
It's a journey for sure.
Right, it's a marathon, not a sprint.
Exactly.
And the article also highlights some of the big obstacles that are still in the way.
Yeah, there are challenges ahead.
It's important to be realistic about those challenges, right?
Absolutely.
So what are some of the biggest things that we still need to overcome?
The technical complexity is immense.
Okay.
We're talking about cutting-edge physics and engineering.
It's pushing the boundaries of what we know.
Exactly. It's not easy.
And the financial investment required to build and operate these systems.
It's a lot of money.
It's huge, right?
Huge.
We need significant funding and infrastructure to make this happen.
Absolutely.
And there's also a shortage of skilled talent.
Yeah, we need more people with the right skills.
In all these fields.
Yeah.
Quantum physics, computer science, quantum engineering.
It's a growing field, so the demand for experts is high.
And then there are the security risks, right?
Right, which we talked about earlier.
Like the ability to break current encryption methods.
That's a serious concern.
That's a real threat that we need to address proactively.
Absolutely. We need to stay ahead of the curve.
Okay, so to sum up our deep dive into the DevHooks article.
Yeah, let's recap.
Quantum computing uses the crazy power of quantum mechanics
It's mind-boggling.
to unlock computational capabilities that go way beyond what our current supercomputers can do.
It's a whole new level of computing power.
And the potential applications are super exciting.
They are
Healthcare, cybersecurity, climate science, optimization.
all areas where it could have a huge impact.
But we still have some major technical hurdles to overcome.
We do.
Building stable and scalable quantum computers, figuring out error correction.
Those are the big ones.
But the key players in the field are making good progress.
They are making steady progress.
And we might see quantum computers outperforming classical computers on certain tasks.
Yeah, in the next decade or so.
But those truly versatile, fault-tolerant quantum systems that we need for widespread use,
They're probably still a while off.
they might take a bit longer.
But it's a journey worth taking.
So a lot of progress being made, but it's definitely a marathon,
It is. It's a marathon.
not a sprint.
But the finish line is in sight.
And that brings us back to that thought-provoking conclusion in the article.
The big question.
Yeah, are we ready for the quantum era?
Are we?
Because it's not just about the technology, it's
Yeah.
about what it means for society.
The societal implications,
Right.
the ethical considerations.
How we prepare for this future where computational power takes such a huge leap.
It's a future full of potential.
It really is. It gives you a lot to think about.
It does. It's a big question.
And for those of you who are interested in learning more,
Yeah, keep exploring.
the DevHooks article also touches on some related areas,
Like what?
like AI-powered cybersecurity,
Oh yeah, that's a fascinating field.
which is connected to those advancements we're seeing in quantum computing.
They go hand in hand.
So it's a constantly evolving landscape.
It is. And there's always more to learn. So
Absolutely.
stay curious.